Morning, Gabriel.
Morning.
Did you have a good break?
Yeah. What's up?
Hey, good morning, Calvin.
Good morning. How's it going?
Good. Looks like you got a haircut also.
Yeah, I did.
Yeah. Nice. All right. Everyone's joining us. Wondering for a minute if it was going to be just me and Gabriel. Yeah. I was feeling like joining at 8 exactly also. Just doing that.
It's right after the break. You got to give us a break.
I know. Oh. Yeah, did you guys all have a good break? Yeah. Do anything fun?
Did a little bit of shooting over the break, so that's always good.
Nice. Do you shoot in Pocatello, like out in Forest Service land, or?
No, I shoot back at my house. We have like 11 acres on a hill, so we just shoot into the hill.
Oh, okay, nice. Cool. Yeah, that sounds fun. Yeah, it was. I grew up in Colorado, so I went back there, but it's been so dry, so it was like I was able to do some like running and stuff at elevations that are normally pretty snowy by this point of the year. So it's a little, it's a little sad to like see them like being completely dry, but kind of nice to be able to, get to do that. So, okay, well, don't have a lot today. I was just, let's see. So on Thursday, this homework is due, the homework 10. So on Thursday, you'll submit it, do the quiz. Before Thursday, I need to release the homework 11, the final homework for you to take. And then also the announcement is, and I'll make this again on Thursday, but the quiz 11. So the quiz 11 will just be to fill out the course survey and submit that. So after you submit it, you should get to a screen that says like either like you completed it or something like this. And so for the quiz 11, you'll just submit a screenshot that's from that completion page. So don't send me a screenshot of your answers. Send me the completion page. So that's what the final quiz will be. So I'll release that too. I believe all of those. I believe the survey was released like during the break for every class. So I'll open that up, and you'll have basically, you can submit that anytime that you want once I open it up, and you can do that. I believe it just needs to be done Probably, I think it's sometime before a finals week, maybe, is when it closes. So that's the only limitation on that, is it just needs to be done before it closes. And besides that, I think I have meetings with a number of you today. So I have four project meetings today. Most of them are right after this class. So I look forward to seeing you all. As I mentioned, they should finish within 15 minutes for each one. But if you are, let's see here, Cade and Mario, you're here. So if I'm just a minute or two late, just please bear with me. It just means that the previous one took an extra minute or two, but I'll be trying to wrap things up so that I can join exactly on time for you. And besides that, I'll mention all of this again on Thursday, as it'll be another class, but to prepare for the final exam, right, it will be cumulative. Most of the questions will be from this transmission line theory work. So these final homeworks, 9, 10, 11, most of the final exam will be on that. But you should count on having at least one problem related to the exam 1 material, and at least one problem related to the exam 2 material. So you won't be completely off the hook for it, but it's not going to be the focus of the exam. Again, you can bring a page of notes front and back to that exam, the final exam. You can also bring a calculator to the final exam. And I don't know. Yeah, go ahead.
How many questions will be on the final?
I have not finished writing it yet, but I would say plan for somewhere between 5 and 8 is about what I'll do. So probably most of the exams I think had what, 4 or 5 questions. So in those ones I gave the normal class period plus a little bit of extra on each one. So there'll probably be at least 1 or 2 extra questions on there. So for example, I would say, that means that you can probably count on 3 to 4 questions about the transmission line theory and 1 to 2 questions each on the other stuff. So usually I write the exam and then I look through it and see if it's like, if there's a bunch of really hard questions, then it might be less. And if the questions are too easy, or not easy, but if I think the questions might be fairly fast to solve, I may, sometimes I add in some questions that are pretty short, which I think you've probably seen on all my exams. Like they aren't as, they don't require as many calculations, but they're more, sometimes they're faster or more graphical or something like that. So I haven't finished writing it, but that's usually the way I do that. Other questions? Okay. And yeah, we'll have Thursday to ask some more questions. Next week, Zayed will be running the class, but you're always, of course, welcome to send me any questions via email. I probably won't, and I'll respond to them as quickly as I can. Next week, I think I may have told you I'll be at a antenna design conference. So that's why I won't be teaching, but the TA will. And that conference is in Singapore, so it may take me about a day to answer any of your questions, but I will answer any questions that you email me. So do feel free to do that. Okay. Yeah, anything else before we get started? All right, so yeah, let's do some transmission line theory. I'll share you the screen. Okay. All right, so this is in homework 10, problem 4. So we did kind of the first half of this homework assignment. And now we're on the, let's see if we can do the last 4 today. So I'll get started. Let's start here. So we have a lossless transmission line, and we're given an electrical length of the lossless transmission line. And it's terminated in a load impedance here. And we're asked to find the reflection coefficient, standing wave ratio, and the input impedance. Okay. So several of these we have done previously. Okay, so right, this one we did before, and this one we did before. So these ones should be pretty similar. However, the next part, the final part, right, is to find the input impedance. So this one is a little bit different, right? So this one we have not seen before and will require us to use some new methods. Once we're done, we want to verify this using module 2.4. And there's some hints here to do this. So on your paper, go ahead and calculate these. So as a little warm up, do these ones we've done before. So if you don't have it, right, you can either go look at the transmission line cookbook, or here. Okay. So go ahead and find these two, the reflection coefficient and the standing wave ratio. All right, anyone get answer?
Got 0.3071. And the angle was 13.5 degrees.
Sorry, what was it? 1.3,
5.
1.35.
132.5.
All right, and that looks correct. What about for the standing wave ratio?
For the standing wave ratio, I got 1.89.
All right, perfect. Okay, so now we have this other term, Zn. Okay, and so this Zn term, right, this is the impedance that we see if we look in right to this circuit. So this is like I'm sure you did some input resistance, right, when you were working on maybe looking at some amplifiers or something. And so you can also do this for transmission lines, right? So you can look into a transmission line and you can determine what the impedance looks like if you're at the end of this. So this transmission line has some length, right? It's 0.35 multiplied by some wavelength fraction. And we can use this information to determine a input impedance. So there's a relationship, right, for this. And it relates the input impedance to the characteristic impedance and also the load impedance. Okay. All right, so this is the equation that you can use for this. Okay, so using the information that you have, you should be able to find the input impedance. Does anyone see, based on what we have, does anyone see any problems or anything that they think might make this tricky to do?
The tangents for me, tangent, yeah.
Yeah, so we have the tangent beta L. Okay, so what do you think we can do to overcome the tangent beta L? Any ideas?
We can reset what beta is equal to.
Yeah, so there are, and let me paste this in. There are a bunch of relationships, right, that between the wavelength, the frequency, the speed of propagation, and then there are some derived relationships, right? Like this beta is actually it's derived from frequency and the speed. And so because this is a lossless line and we can assume that the wave speed is at the speed of light, right? We can see here that the beta, right, is given in the most complex form as this. However, do we have any reason to believe that the relative impedance is something else? Let's see. Or maybe put it a different way. Can we rewrite this in some ways that simplify it? So, right, beta L, right, could be written, right, 2 pi f all right. And right, we see here, right, this relationship. Okay, well, this looks like this, right? Does everyone see this? So this is kind of like, I mean, this is 1 over lambda, right? And what about our transmission line length? What was that given as?
0.35.
0.35. What else? Lambda, right?
Lambda.
Yeah, it's given, this transmission line length is given as a fraction of the wavelength. So do we actually even need to know the frequency?
No.
Yeah, we don't actually even need to know this. What about, do we even need to know the speed of propagation or the dielectric constant inside of this?
No, we really don't.
Yeah, and this, you don't actually. And that's one of the things that makes a lot of this transmission line theory very interesting, is that there's certain ways of abstracting the information where we could actually, if we needed to, we could deal with wavelength fractions instead of things like the frequency, or we could be given you know, transmission lines where we don't actually know how fast the wave is propagating. It could be filled with a very exotic material. And there's actually ways, right, where we can, right, use that to our advantage and deal with things on a beta L basis instead of dealing with it on a basis of knowing the exact frequency. So I know it's a little, you know, tricky, but the main thing to take from this is that there are a lot of these constants and relationships when you're dealing with waves. And if you're clever and you're dealing like a real life experiment, or you have a real thing that you're working with where you don't know every single unknown, you can sometimes combine the unknowns in a clever way so that you can kind of go past that. So basically, in this case, right, our beta L, if we know the length in a fraction of the wavelength, then we can actually, right, get this to cancel out, right? Because this is going to be 2 pi over lambda multiplied by 0.35 lambda. And so we don't actually even need to know what lambda is in this case, right? So for us, the beta L is going to be 0.35 times 2 pi. Okay, so using this information, you should now be able to find Zn. Now, one more question. What form of complex number do you think we should represent this input impedance as? And by form, right, I mean, we have like polar, rectangular, etc. What form do you think we should present this in?
Probably rectangular, because that's what ZL is given to us in.
Yes, very good observation. So because ZL, right, ZL is often a complex number. And when we're dealing with ZL, right, we think of it as an impedance, and we're used to that being given as a rectangular format. And for one reason or another, right, this often makes sense. And usually that reason is that we like to think of this in terms of lumped circuit. So what do I mean by that? I mean that a lumped circuit right? If we're given a ZL, we could write it as a black box, right? And this is the very simplest way. Or we could write it as a lumped circuit. And right, if we have a plus J30, right, this means, right, we could write this like a resistor and an inductor in series, right, where we have some real plus some imaginary. So this lumped circuit, right, is convenient for us. And of course, right, this ZL could be very complicated, right? Can you imagine a situation where we have, I don't know, a resistor, and then we have capacitor and an inductor, and then another one like this? You could imagine a situation where we have a very complex form of elements, circuit elements, or structural elements that make a capacitor and an inductor. But the lumped circuit model means that we just lump it all together into a very basic form where we just have resistance, a real part and an imaginary part. So this Zn and many impedances, right, we like to write them in rectangular form because we want to think of them like a lumped model in many occasions. Okay, so take a minute now. Maybe you've already done this while I was talking, but see if you can calculate what this Zn is and write your answer in rectangular form. And, as I mentioned, I think last week, if possible, I would recommend putting your calculator into rectangular mode, and that will probably make it easier to get this result. All right, so go ahead and do that. Let me know when you have finished and gotten a final answer.
I got 61.46 plus J32.80.
You're muted, Dr. Chrysler.
Thanks. Daniel, is it 61 minus J32? Is that what you?
61.46 plus J32.
Okay. So I'm thinking you're gonna get a negative here. This is actually somewhat close. I think it should be closer to 61 minus J32. So see if you can take another minute and get that. All right, anyone else get something?
So for mine, I ended up getting about 64.8 minus J38.
That's what I got too.
Yeah, that's what I'm getting. Yeah, okay. So, and I think for the sub parts, I just calculated it, you should get 100. And if you go to the top, let's see, 60 minus. Did anyone break it down this way? Did anyone break it down like that? Do any sub calculations? All right, well, it's fine if you didn't, but if you do, this is what the first inner expression should be, and the denominator inner expression, and you should get 64.8 minus J 38.3. Okay, so if you did not get this, go back and check. Make sure your calculator is in radians, right? So you should be in radians and in rectangular. All right. Any questions? All right. So did anyone get the module running and check it on the module? All right. If not, right, just follow what we did previously. Input your correct characteristic impedance, the load impedance that you have, and then I recommend choosing a line length of 0.35, and then you can use the slider. And up here, there's two sliders. This one is changing, and you can see here, right? It's changing the wavelength. The other slider does something similar, but it is a little different. So I'd use the top slider and move the slider all the way over to the left. And you can see now, right, that we've moved the slider, these green arrows, we've moved it all so that we're all the way over here, and we're looking at a distance or a length, right? So we're now at a length of 0.35 wavelengths. Like we were discussing, right? It doesn't actually matter what the relative permittivity or the frequency are, because we're at this 0.35 wavelengths. And now if we come over here, we can see the impedance. And this is the impedance that I just calculated, right? So this is the verification. Let's check to see if what I said was true. Let's change this to 3. I'm gonna hit update. Okay, so we're here now, right? Our cursor is here. Let's change the wavelength. So I'm moving this over until these green arrows are all the way over at 0.35 wavelengths. And then let's look at the input impedance. So this is the impedance that we see when we're at the point of the green arrow. And it turns out, right, that it is identical to what we just calculated. So just like we postulated, it does not matter what our frequency is. Let's change this to 5 and move it all the way back again. And look, it does not matter what the relative permittivity is. We will get the same input impedance when we were at the same distance in terms of the wavelength fraction. So the input impedance is not actually affected if you have a line length that's given by a wave fraction, then the input impedance is not actually affected by the frequency, relative permittivity, or the speed of propagation on it, so long as the wavelength, so long as the transmission line remains that same wavelength fraction. Yeah, so kind of interesting, right? Any questions about how to use the module? Yeah. So now let's look at another problem. So now we have a voltage generator, and we know something about the voltage generator. We know the internal impedance, we know the frequency, we know that it's connected to a 50 ohm lossless airspace transmission line. So when this says 50 ohm lossless airspace transmission line, what is this? What are the pieces of information that we can get out of this? What is characteristic impedance?
Ohm.
All right. What is the relative permittivity?
One.
1.
And what is the velocity of propagation?
Gonna be the speed of light.
Yeah. Okay. So we actually, this small statement tells us actually quite a few things, right? And now we also have a line length and a load impedance. So the first thing, see if you can find the reflection coefficient. Let me know when you have this. This one should be getting pretty fast to this one now, right? Put our calculator into polar mode and punch everything in. So let me know when you have this.
Zero 0.690 degrees is minus 9.74.
Did you say 90 degrees?
No, negative 29.74.
Okay. All right, perfect. This is what I got. Okay, so now what about Zn? What can we do to calculate Zn? So do we have enough information to determine beta L this time?
Yeah, we have all the information we need.
Yeah, we do have enough information this time to get beta L, right? Because we know, right, this is L. So L is 5 centimeters. And this expression Do we know what the frequency is?
10 gigahertz.
Yeah, not exactly, right? So we have it from here. This is the all right. So you should be able to find beta L, or simply just beta. So first, maybe, right, we can do the calculation for beta, right? So this would be 2 pi times 10 to the 9th over 3 times 10 to the 8th. Does anyone have a number for this?
Well, just simplifying it from where it is, it'd be like 20 pi divided by 3.
Yeah. So we could write beta like this. All right. And do note, I have dropped the units, right? But this is in radians per meter. So we either want to convert this to centimeters or convert this, right? And notice, okay, this is 0.05 meters. So sometimes even, right, it may be useful to just figure out a full expression for what beta L is. Does anyone have that? Getting like 1.07 radians. Okay. All right, so now see if you can find an answer for the input impedance. Okay, so use the same method that you used the last time. Just put everything into this equation. Let me know when you have a final result in the rectangular form.
Okay, so for what I got 12.5 minus J 12.7.
Okay, I think this might be, I think the first part is correct. Oh, yeah, never mind. Sorry, yeah, this should be correct. Yeah. Okay. So did anyone else get this?
Yeah, I also got that.
Okay, perfect. And then it's just about finished with marking the rest, but I think we should probably just move on. So this is what you should get. Again, if you need help, make sure your calculator's in radians, break it down to the top part and the bottom part, and that might help you simplify just a little bit. Okay, so what about this last question about the phasor domain? Okay, so in this question, we want to find the input voltage and the input current. Okay, so we can do this by doing all these calculations in the phasor domain. All right, and we can basically think about this. Where we want to find, right, what the voltage is here. Right, where this is the input voltage. Okay. All right, so can anyone think about how to do this? And also too, remember, we've already figured out what this is, right? So right, we do have an input impedance here that we can kind of simplify this down to even. So take a minute and see if you can think about this from a circuit perspective on how we could determine what the input voltage is. I guess too, to make this more clear, right, we can really write this like a circuit, right, like this, where we have a generator, a generator impedance, and an input impedance, right? And we're trying to find the voltage here. So what circuit technique do we know that we can use to find that?
Divider.
Yeah, right. We can use the voltage divider. Where we have the generator voltage plus this. Okay. Now, let's see, anything else we don't know? What is the generator voltage? What is the generator voltage? What should we have this as for the?
5 volt.
Yeah, this should be 5 volts. Right, and that's what doesn't have any phase angle on it. Okay, so take a minute and see if you can calculate the input voltage. And sorry, before one more thing, what should this will be complex? How should we write this? What complex form should we give the voltage in? Let's start with, should it be rectangular or polar?
It should be polar, shouldn't it? Because it's coming out in voltage.
Yeah, so we almost always give, right, voltages and currents are going to be in a polar form. And what about, should we use it degrees or radians? How do you typically see voltages given, phase voltages?
Typically, they're in degrees.
Yep. Yeah. Okay. So take a minute and calculate the input voltage in polar form and in degrees. Okay, anyone get an answer? I got 1.39. Anyone else get this?
Yep.
All right,
So I just got.
Yeah, same.
right. Now, what about if we want to know the current? What should we do if we want to find this phase current? What could we do?
We can just divide the voltage by the input the input impedance.
Yeah. Okay, so let me know when you get a result for this.
Okay, I got 78.4 e to the j 11.5 degrees. Yeah.
Yeah. All right, and what are the units on this?
For that, it's gonna be in milliamps for me.
So 0.078. All right, this is the answer that I also get. All right, so we can also, if we know information, right, if we know information about the generator, we can additionally break this down even further. So remember the purpose for this, right, is we have some circuits have a frequency that's high compared to the length, right? So that was some of the first problems that we did, right? We looked at what happens, right, if you divide the frequency by the transmission line length, right? And if this, depending on what this ratio is, right, if the frequency is very high and the length is very small, then we're going to need to deal with this circuits as a transmission lines theory circuit. And so that means all of those pieces, we have some input with the generator. The generator has some actual resistance to it. Then we would have a line, a transmission line with some length, right? And this is some unknown length that it has to travel through. So we have some impedance, some voltage generator, and then it's connected to some load, right? And this is a complex load. The length of this line is given by the characteristic impedance. We may also know some information about the relative impedance of the permittivity, relative permittivity of the line. We may also know something about the speed that the wave propagates along this line. All of these things could be used to get beta, right? The voltage generator would be used to get omega. We can calculate here a Zn. If this is lumped, right, we can use our knowledge of circuits to determine a lumped impedance. We can simplify all of this to learn things like what is the input voltage, what is the current here, right? What's this phase current, phasor current? And whenever we have a circuit, right, where we have a high frequency and a small wavelength, a small length that the wave must propagate on, we must take all of these things into account when we're doing the circuit analysis. So hopefully what you get with the point, or like what we're getting to here is, right, this is what we learned to do in probably the first circuit class that you took, right? You learned how to do voltage dividers and analyze very simple circuits. But what electromagnetics and microwave engineering tells us is that if we have high frequencies and the wave needs to travel long distances compared to it, then we're going to need to take in a few extra steps before we get to the point where we can perform these simple circuit actions. We're going to need to take into account the length of the line. We're going to need to find beta, which is based on the propagation of the wave. And we have many different methods to solve for this. All right, so before I go, I just wanted to mention that. Do you have any questions about this? The things that we've learned? All right, the last problem, right, is this problem where we have something in parallel, right? So we have two loads. Right, we have load 1 and a load 2. Right, we know the length of these. And what we're really trying to do is we're trying to find this. So can anyone think of a strategy that we should use to find this Z in?
Well, I would say first find like the Z in of both antenna legs or the.
Yeah, so from right here, right, we can find ZN1. And from here, right, we can find ZN2, right? Because we can determine a beta L2 and a beta L1, right? We know the load and we know the characteristic impedance. So that if we did that, right, we could simplify this problem into something that looks more like this, right, where we have ZN1 and ZN2, right, where these are just in parallel. And then you can find and then this is equal to something, right, some load, we could call it like the load prime or something like this. And from here, right, you could use the final, we know this this line length as well. So you could calculate the overall input impedance on this whole thing. Okay, so find the impedance for this first antenna, find the impedance for the second antenna. Then those two are in parallel. So find out what the total impedance, total parallel impedance is. And then that becomes, right, essentially, you would just be taking this whole section, right, and transforming it from this complex situation into one single lumped together load impedance given by both of the transmission line lengths and both of the antenna loads. And then you know this distance here, so you can calculate that Zn. Okay, any questions? All right, well, I hope you all have a nice day, and I will see you all on Thursday. And I look forward to seeing several of you later today for the project update meetings. So I am going to get off now and join the first meeting with Calvin. So I'll see you all later.
Good question, Dr. Chrysler.
Okay. Yeah, I don't have a lot of time today, but one.
I just want to ask, I saw you're listed as an advisor.
Okay.
Can I send an email regarding that?
Yes.
Okay.
Yep. You can email me and I can give you some advice about classes or whatever. Yeah. All right. Thanks.